Alright, I'm making this video to help you review for your test and also to review some concepts that are troubling to some students and some students continue to make mistakes on. So hopefully this will help you by giving you something to study and look at in preparation for your final test for Chapter 1. The first thing we're going to do is take a look at this function, f of x equals the square root of x minus 2 plus 4. We are going to do a whole bunch of stuff to this function to help us review. So let's just start by thinking about what function does it, what basic function could we compare this to? Fairly quickly, I'm sure that you would come up with the basic function square root of x. Well, let's talk about what these numbers that have been added into this function do to it. If we look at the minus 2 here, that is going to shift our graph horizontally. So that's going to be a horizontal shift. And then remember, when it's within the function and happening to the x itself and not the entire function, that's a horizontal shift. So when we subtract in that horizontal shift, that is actually going to move our function to the right. And this plus 4 out here, well, that's going to give us a vertical shift because it's like adding 4 to our basic function to the entire basic function. And when that value is positive, that's going to be a shift up. In this case, 4 units. So what would this graph look like? Probably without even graphing on your calculator, you should realize if we take our basic function, which looks something like this, and we shift it right 2 units and up 4 units, we're going to get something that looks the same. It's just starting in a different spot. So to the right 2 units and up 4 units. Basically, that function's heading up this way. Obviously a real rough sketch, but it's really all we need to answer more of the questions that we're used to answering. So what intervals is this function increasing, decreasing? Well, this function, so basically what you're going to do every time you're asked this question, I like to just take a vertical line, in my mind, move it across the graph from the left to the right, and then once I get to the graph, if it takes a little while, well, does the graph go up or does it go down? Well, it's going up, and it's going to continue to go up forever in its domain, so we are going to be increasing and never decreasing, and the interval would be from 2 to infinity. That brings up something else we definitely talk about a lot. What is its domain? Well, we just answered it. We had to realize that in order to say where it was increasing. But our graph, its domain is from 2 to infinity. How do we ever get domain? Well, we take a look at our basic, or not our basic function, but whatever function we're dealing with, and look and see if there are any restrictions. The restrictions that we have are there any square roots? If there are square roots, am I putting numbers in to the square root that would give me a negative answer? Because I cannot. So if there are numbers that could give me a negative answer, I cannot include them in my domain. Other restrictions you got to look for, am I dividing by 0? Or is there a number I put in that would make me divide by 0? And then the third one now are the natural log functions. You cannot put in any number that is 0 or negative into a natural log, so you have to consider that when talking about your domain in those functions. So in this case, the square root cannot be less than 0. So the work for domain would be, if I take what's under the square root, what would I have to do to make sure that that is greater than or equal to 0, is the question. Well, simple inequality problem solving here tells us that x would have to be greater than or equal to 2. How do we write that? The domain is from 2 to infinity, including 2. You'll notice on the increasing interval I used a parenthesis instead of a bracket. I would allow you to use either. For range, we need to look at the y values. What y values does the graph hit? Similarly, you could take a horizontal line on your function and start from the bottom and work up. What does the graph hit, or what does it not hit? Well, it did not start until we got to 4, and then it's going to go up from there forever. So that tells us that our range actually starts at 4 and will continue on up forever. Try to clear up some room here. Keep most of this stuff on the screen at the same time. Okay, so another thing that we can take a look at is we can look at, is the function continuous, or does it have some sort of discontinuity? Well, for that, if it has some sort of discontinuity, we're talking removable, jump, or infinite. Removable would be where you draw the function, let's say the function something like this, and then all of a sudden there's one point missing and it continues as if you were drawing the whole thing out, and it's removable if you are drawing a function and basically one point is missing from a continuous function. That point could be located above or below the missing point. That's removable. It's a jump if your function looks continuous and then you pick up the pencil and actually move vertically either down or up and continue the function from there. Infinite is where the function will start to decrease or increase towards negative or positive infinity and then start again in the opposite direction. That would be an infinite discontinuity. In the case of our graph, a square root, it is continuous. This is considered continuous on its entire domain, domain being from 2 to infinity. So it would be continuous to us. Another question that we could think about is the function odd, even, or neither? Well, when considering that graphically, the function would be even if it reflects onto itself in the y-axis, and it would be considered odd if it reflects onto itself through the origin. Well, in this case, neither of those things are going on, so it is neither graphically. Algebraically, you could figure that out by plugging in a negative x for every x in the function. And in so doing, if it equaled the function itself, or the function that you started with, it would be even. If it equaled the opposite of the function that you started with, it would be odd. So basically, when I plug in that negative x, if I got the square root of x minus 2 plus 4 back out, it would be even. If I got the opposite of the square root of x minus 2 minus 4, it would be odd. So when I do that, you'll see I don't actually get either of those answers. And that's why it's neither. It's neither odd or even. So on this graph now, let's take a look at horizontal asymptotes. Anytime I ask you to talk about horizontal asymptotes, I'm also asking that you can talk about the end behavior of the function. When working with answering a question like this for horizontal asymptotes, you are always going to write the limit as x approaches negative infinity of the function f of x, in this case, and what that equals. Well, remember our graph. It's up 4 and to the right 2. Well, this is basically, again, you can take a vertical line if you'd like to help you across here. And as you go to the left, as you're heading towards negative infinity, where is the graph going? Well, in this case, it's not going anywhere. There is no graph as you head towards negative infinity. Because of that, you would write does not exist. That limit does not exist. Even if that would have existed and it would have approached a number, you would still also do the other work. As x approaches infinity, what does the function do vertically? Well, so in this case, I'm going to take my vertical line, and as I go to the right, what's the function doing? Well, it's going up. It's going to keep going up. It's not approaching any specific number, so it's actually approaching infinity. What does this tell us? Well, since this was not a specific number, like 1, 0, 2, 18, negative 4, it wasn't any number, and this wasn't any specific number, we only needed one of them to be a number. Since neither of them were, there is no horizontal asymptote. If even one of them was, well, then we would say y equals whatever that number was. In this case, there isn't one, so there's no horizontal asymptote. We've already talked about this a bit, but I'll just bring it up here again. How does this graph relate to one of the 12 basic functions? Well, when you're asked that question, you always are going to say which 12 basic function it relates to. In this case, it's the square root of x. And then you say what happens to the square root of x. Well, it's the square root of x shifted right 2 and up 4 units. That would be the answer to how does the graph relate to the graph of one of the 12 basic functions. I could also ask you what the inverse of this graph is, or of this function is. Remember, when you're finding inverse, you're going to take and you're going to switch the x's with the y's and the y's with the x's. Remember, f of x is just like saying y. So I'm going to switch that with an x. And then that y that's inside the square root, I'm going to switch, or that x that's inside the square root, I'm going to switch that with a y. And then I'm going to solve for y. Well, basic algebra from here, I'm going to subtract 4 from both sides. And then I'm going to square both sides. And of course, when I do that, I'm never going to say that this equals x squared plus 16 or minus 16, because that is crazy. You would never do that. And at this point right now, I'd much prefer you get everything to one side first so that I know that you could have had the equation then just tried to go too far with it or made a mistake when trying to simplify. So the last step would be just to add that 2. Okay, so now at least you have the correct equation written down. I would expect that you could simplify this quite easily. So that would be your inverse function, which actually could be written as f inverse of x, and would be. Now, what you have to be careful with on this is that you have the appropriate domain stated. You cannot just write this and say this entire function is the inverse of the function we've been talking about, because it's not. One thing that we talked about in class was you have to carry the restrictions from the function into the inverse function. The restrictions that I'm talking about have to do with the range of the original function. What restrictions did we have on the range? Well, if you remember back, the range was from 4 to infinity. The domain of this inverse function would need to be from 4 to infinity also. That should make sense to you, because you should know that if you're talking about a square root function, well, that's only going to be half of the parabola that you would have if you did plus or minus the square root function. That's why our domain is restricted in the same way now, because we only want half of this parabola inverse function in order to be the inverse of the square root function that we've been talking about. Well, that was quite a bit of fun. So here's another one. I'm going to quickly go through some of those basic things again. Let's talk domain. Do I know what the domain of this is right away? Yeah, it's going to be all real numbers. Why is it going to be all real numbers? Because at quick glance, there's no restrictions on the x's that I can put in. I can put anything into those. How about the range? Well, here's where I have to be careful, because I remember this looks like one of my basic functions. The function I'm talking about is the absolute value of x. Well, I know that the range is restricted on that because that function only goes from 0 to infinity. Well, what happened to this function, or what happened to this basic function? Well, this negative 2 right here shifted it down 2 units. This plus 3 right here shifted it left 3 units. This 2 out here gave it a vertical stretch by a factor of 2. So now my new function is going to look something like this. And what does that mean to me when I'm talking about finding the range? Well, it means that now, instead of being from 0 to infinity, it's going to be from negative 2 to infinity. Let's talk about intervals of increasing, decreasing. On this function, since we know this lowest point here is going to be a point where the graph changes from either increasing to decreasing or decreasing to increasing, we we really just want to know what is the x value at that point, and we know it's -3. So what I always do is I take that vertical line, always going from left to right, and see what the graph is doing. Okay, I've hit the graph. It's decreasing, decreasing, decreasing until this point. Okay, so I would write down decreasing on the interval -infinity to -3. Then what happens at -3? Obviously, if that's where something happened, it now is going to be increasing from -3 throughout the rest of the graph. So that's what you would write, increasing from -3 to infinity. We can also talk about local min and maxes. Any points where the graph changes from going down, from decreasing to increasing or increasing to decreasing, that's when we have mins or maxes. Well, in this case, we have one min, one minimum. This actually is an absolute minimum because it's the lowest point on the graph, as opposed to a local minimum. I'm not concerned that you know that and will be able to state that, but it's a little extra information for you. It's always good to know more than what you absolutely have to know. So that's a minimum. When I talk about the minimums, I would write all of them down. In this case, there's only one, and so I would write down its coordinate points, -3, -2. That's the minimum. That's the extrema that it has, that one point. We can talk about it being odd, even, or neither. Normally, the absolute value function is an even function because it can be reflected in the y-axis. This one, though, has been shifted to the left, which means it's going to be neither. It does not reflect upon itself when you reflect in the y-axis anymore. For horizontal asymptotes, again, you would write down the limit as x approaches -infinity of this function. This time it's called g of x. That means what's happening as you go to the left. Well, that graph is going up, so it's approaching infinity. You'd also write down the limit as x approaches infinity of g of x. What's it doing? As you go to the right, it's increasing, so it's approaching infinity. Since neither of these are actual numbers, there is no horizontal asymptote. One thing I did not mention in the last problem was talking about if the function's one-to-one. This function, well, how do you tell if a function is one-to-one? Which basically means every x value is mapped onto one y value and every y value onto one x value. Another way to put that is, does it pass the horizontal line test and the vertical test? Well, this function would not be one-to-one. It passes again, we're looking at the blue function here. It passes the vertical line test. However, it does not pass the horizontal line test. As I go from bottom to top, there are many, many points where the horizontal line will hit more than one point. So if that's the case, then it is not one-to-one. It is a function because it passed the vertical line test. It is not a one-to-one function because it does not pass the horizontal line test also. Another problem that some students were confused with is when I asked you to determine whether the formula determines y as a function of x, that's basically saying, is the formula a function? Well, in this first example here, very quickly you should recognize it's a parabola. So yes, parabolas are functions. If you weren't sure, you could graph it, and once you graphed it, you would try the vertical line test, and you would know that it is a function. On this one here, y squared is a good indicator that it's not going to be a function. but you can do some work to verify that. Subtract 9 from both sides. I'm sorry, add 9 to both sides, and then square root both sides. Remember that when you square root, you need a plus or minus here, and because of that plus or minus, that basically says in order to graph this equation, you would need to graph y equals the square root of x plus 9 and y equals the opposite of the square root of x plus 9, which would mean you need two functions to graph to make this formula work, and that's basically telling you it's not going to be a function. And you probably realize that because last year you learned if you have a y squared, that's going to be a horizontal parabola, which would not be a function. Next, I'd just like to review compositions. If I asked for g of f of x, in either of these ways, that's saying take the function g of x, and anywhere that there's an x, replace it with f of x. So I'm going to take this function here and I'm going to rewrite it. As soon as I get to an x, I'm going to stop and I'm going to write the other function in. So here, I'm going to start writing g of f of x. And then now right away, I'm going to have to stop. And instead of writing an x, I've got to put that entire function in. And then I just have a minus 1 at the end because I've written x minus 1 only instead of the x, I had to put the other function in. So g of f of x in this case, quite simply, is 3x squared plus 4x. And then you're done, because plus 1 minus 1 is nothing. Another thing I wanted to do is take a look at a function where we can look at just focusing on the asymptotes. So here's a function, say y equals x squared plus 6x plus 9. That entire quantity divided by the quantity x squared minus 1. Well, first of all, before I even graph this, what I would expect is, since I can factor this, I can factor the top or and the bottom, but what I'm really interested in is where I would get an undefined answer. And on the bottom, if it's x squared minus 1, well, I get that by taking x minus 1, x times x plus 1, which tells me x cannot equal negative 1 or 1. So that's where I would want to look and see if there's vertical asymptotes. And then also from last year, you realize since the numerator and denominator are both degree 2 polynomials, or the highest power is 2, I would take a ratio of the leading coefficients to see where I would have a horizontal asymptote. So I would expect a horizontal asymptote in this case, since the leading coefficient is 1 on the top and a 1 on the bottom. I would expect y equals 1 to be a horizontal asymptote. Let's take a look at a graph of that. So I plug that in. If I go to my graph, I always just do zoom 6 right away. Here's my graph. And basically, what I'm seeing here is it looks like the graph is coming down here as I'm going to the left. Looks like it starts to come back up. So I would look on my table when I go get a really big number in there. Am I getting closer to 1 like I expected to the left? And as I go to the right, as that's decreasing, is it approaching 1 on the right as well? That's what I would expect And then I'd also be looking at a vertical asymptote here at x equals -1 and a vertical asymptote at x equals +1, because what that's what I expected. That's because that's where I cannot plug in those x values. Notice also on the bottom here there's a little graph, which would mean I would expect this to continue down forever and this to continue down forever, but not cross over the x equals -1 and x equals 1 lines that I've previously mentioned. So you can look at that graph a little closer on your graphing calculator. I'll write down the work that's needed. So for the horizontal asymptotes first, I would need to check the limit as x approaches -infinity of my function. That's an x, by the way. And I would need to check the limit as x approaches +infinity of my function. And for the vertical asymptotes, I would need to check the limit as x approaches -1 from the left of my function. And I'd have to check the limit as x approaches -1 from the right of my function. See what each of those equals. And I've got another set. I need to check the limit as x approaches 1 from the left and for that same spot the limit as x approaches 1 from the right. So if you look at the graph, here I can probably bring it up also. I'm not going to zoom over to the side. I think you can do that. But I'll just bring this onto the screen so that you can see it while we're talking. And when I say while we're talking, obviously I mean while I'm talking to myself and you're just viewing this video. If you start with the horizontal asymptotes, as you go to the left, you're going to see what I described. It does come down, but all we're concerned with is that what happens as you go to the left as far as you could imagine. Well, as you get farther and farther to the left, you're coming towards the value of 1, but never hitting it vertically. So as you go to the left, you are approaching 1. And as you go to the right, the same thing is occurring. You head to the right, you actually are getting closer and closer to the value of 1, but you're not going to actually hit it. That means that y equals 1 will be a horizontal asymptote. Now, when we look at this vertical asymptote that we think there's going to be, I'm approaching -1. So as I approach this vertical line from the left, this graph is heading up. So that's infinity. As I approach this value of x from the right, well, now I'm coming down here and that's actually going down to -infinity. All I needed was one of those to be either infinity or -infinity to say x equals -1 is a vertical asymptote. And then finally, checking the other one, I'm checking the same thing here. I'm looking at this x equals 1 vertical line. That got a little crazy, sorry about that. As I'm looking at that, right here, I'm talking about approaching 1 from the left. So that's looking at the portion of the graph down here. Well, as I approach 1 from the left, it comes up, it comes back down, and it's going down towards -infinity again. As I come from the right towards the x value of 1, well, it's going towards +infinity. Again, all I needed was one of these to either be infinity or -infinity, and that would tell me x equals 1 is a vertical asymptote.